Welcome, this is Professor Nathan Weezy of Marquette University. In this section, we're going to talk about single-phase PLL using a fixed point Q format for digital control of power electronics. So we're going to use the same PLL structure for a single phase that we used in the first description of this, except for now we're going to implement this with digital controllers and talk about the difference, and also talk a little bit about some Matlab code I used to generate this. Okay, so the structure is going to be exactly the same, except for our controller is now in the Z domain, and our integrator is, look at that, a backwards Euler integrator. Okay, awesome. Other than that, nothing's different. I will say that we're going to use 32-bit numbers. Okay, so we're fixed point. And the point actually happens to be, in this case, I believe Q21. So the first 21 digits of our number are going to be fractional, and then we'll have one bit for sign, and the rest of the bits will be for integer above the sign. Okay? All right. So we designed a controller last time. We're going to use our low-pass filter here. So these numbers are directly from the last discussion using single-phase PLL in continuous time. Now, what I'm going to do is talk a little bit about some of the Matlab code that I used to generate this. So first thing I did is I cleared everything out and I generated some symbols. So that you need the Matlab symbolic toolbox to do this. It'll just set S, omega P, K, and P as symbols. I wrote some transfer functions. Of course, GOL is the transfer function, the open loop transfer function for a PLL. I also wrote the closed loop transfer function here so I could see what it looked like in terms of with no variables, and just look to see what it looked like. So go ahead and clear all that out. I took the transfer function of S and set it equal to S. Bode options is pretty nice. What I'm going to do is go ahead and make everything in hertz, because I like to look at Bode plots in hertz, and then I kind of set the limit for that. So that's what these lines do, and it's just stored in an ops structure that we can pass into Bode later. This Kvco gain equals 1. This is the gain of the voltage controlled oscillator. I just have it scriptable. I know I set it to 1 in our previous discussion, but when we go to implement this maybe in a different controller, Kvco may not be 1, it may be 2, 3, or 4. We can just change it quickly here and go through. FBW, this is the bandwidth of my controller. Again, this is a variable selectable if I want to change it to change my controller. Theta is a damping ratio. That's 1, again, selectable. Omega is the bandwidth frequency in radians, so it's just 2 times FBW. Again, that's going to be selectable. If you look at A, B, and C, these are just numbers of the, these are the numbers in front of the polynomial in the denominator of the closed loop transfer function. So if you look at the previous lecture, these are what they are. And the reason I write them as ABC is because I'm going to solve the quadratic equation for them so that I can get the gain K and the position of the filter gain omega F for the low pass filter. So essentially you can see K1 and K2 are just the solving the quadratic equation, assuming A, B, and C are the coefficients of the second order polynomial. Now once I solve it, what you'll see is K1 and K2, this one's the one I'm going to use. K2 turns out to be negative, so that doesn't work. Once I have K1, I can solve for omega F. So none of this stuff is new. This is just written in MATLAB, and this is how I solved for K and omega in the previous lecture when I did continuous time. It's just now that you're looking at my script, you can see what I'm doing, how I'm solving it, and also that I'll be able to change again certain things if I want to adjust stuff later. So at this point, at the end of line 25, I actually have the design of my low-pass filter that will achieve a bandwidth of 10 hertz and a damping factor of 1. And what's going to happen now is I'm just going to check some stuff and convert this to a digital controller. So line 27, what this does is create a transfer function object within MATLAB, because S is a transfer function. Omega F and K1 are the gains of our low-pass filter. And what I'm going to do now is go ahead and convert this to a digital controller. This is also adjustable. TS is the sample time. This is when you're on a microcontroller, essentially this is how fast you're running control loop. You're updating the controller every in this case, 10 kilohertz or 100 microseconds. So you can change this to scriptable. For now, I'm just going to do 10 kilohertz. It's a good update rate. And I'm going to convert these things to digital controllers. So I'm going to create another transfer function, capital Z, which will be the transfer function of Z with a sample time of TS. And this just gives me Z so I can write the transfer function out of other things. You'll see here in a second. So I'm going to define S back as the backwards Euler transformation or approximation. Remember, we had this from a couple lectures ago that we're going to approximate S in the backwards Euler format as this. So that's essentially what I'm doing. I'm creating S back as that. And then what I'm going to do now is I'm going to plug that into the low-pass filter right here. And GC dig backwards will be my digital controller. And then I'm going to do it for a couple other ones just to check some things. So I'll create a zero order hold one. So there's a fancy there's a very fancy command for Matlab that will do some continuous times to digital transformations for you with some very simple inputs. So you can pass in the function you want to convert, the sample time, and the type of conversion you'd like to do. Well, they don't have all of them. For instance, they don't have a backwards Euler, so I did that on my own. But I'm also going to check the zero order hold and the Tustin, which is one that we've gone over before. So essentially what I have here, line 32, 33, 34, are 3 digital controllers that are all approximations of a low-pass filter. One's using backwards Euler, one's using zero-order hold, and one is using Tustin, or the bilinear transform. Okay, now this next line of code, so essentially after I'm done with this, I actually have my line 32 through 34, I have my controllers designed and done in the digital domain. Now what I tend to do is I have this code directly in C. So what I do for lines 37 through 55, I export these numbers of these controllers directly to C code. I'm going to show you what happens. So if you look at 42 through 45, I'm going to F print a bunch of integers, which are coefficients of my digital filter. Those coefficients are coming from GC dig backward and GC dig Tustin. I'll show you what happens when you run this code. I think it'll make more sense when you see the output. So lines 1 through 4 here are the output of lines 37 through 45, which essentially give me the 4 numbers of my filter for a backwards Euler approximation of a low-pass filter with a bandwidth of 10 hertz and a damping ratio of 1. Now look at, you see these numbers, they're quite large, but remember, this number is in Q21. Okay, that's interesting. So if you want to know what this number really is, you take 2151392 and divide it by 2 to the 21, and you'll get the number it represents. And the same goes for all these other coefficients. Okay, so that's fixed point. Now I do it again, I run this, here's the ones for Tustin, so that'd be lines 47 through 55. You can see the coefficients come out a little bit different. Different approximation, different numbers. Okay, again, they're both different approximations for the low-pass filter. So I'm going to run the digital controller for both of these filter structures. See what happens. Okay, first one that I'm going to do, let me step back for a second, is the backwards Euler. And if you look at my coefficients here, that'd be these 4 here. That's what this represents. So what I'm telling you here is that for B1, this 2203593, if you divide, here, let's write it down, just a sanity check here to check Q21, 2203593, and if you divide this by 2 to the 21, what this is equal to approximately is 10.51. So that's a coefficient up here. And of course, there is no constant term, so that's why B0 is 0. Okay, so just to give you a sanity check on that. So these coefficients for a fixed point Q21 right here are really implementing this controller down here. Okay, cool. Let's take a look at our response here. This is again for the low-pass filter. You can see right away we're behind. We're going to catch up. Our PFD is saying speed up, speed up, speed up. The control effort looks almost exactly the same as it did in the continuous time, except for if you zoom in and look here, you can see it's digitized because we are sampling at 10 kilohertz. So we're running a control loop at every 10 kilohertz. So after a couple cycles of 60 hertz here, you can see we're pretty well locked on. Once we get into here, we're just teeter-tottering back and forth. Though the width of this is just one cycle. So we're at 10 kilohertz, it's 100 microseconds. And essentially that means we're in the stable region, or we're stabilized now, locked on. Let's take a look now if we go ahead and run this for the Tustin approximation. So you can see the controller is a little bit different when you look at it. But let's just look at the output. Again, we start with this, we're on locked phase. The PFD is saying speed up, so we're speeding up. You can see the control effort is speeding up. And then you can see we teeter-tot and back and forth on the PFD between speed up and slow down. And it's one cycle wide, and one cycle, the cycle length I'm talking about is the sample time, or 100 microseconds. So once again, we are locked here. We're locked from here on forward. From here, this is kind of the lock state. And there's no discernible difference here in terms of looking at these waveforms, whether one's better than the other. They're just different implementations of the same controller. All right, so let's now take a look at the low pass, the PI controller. We did do that. So here's my code. Line 1 through 17 is my code for designing and selecting the gains for the PI controller. Again, scriptical, my damping is 1, my natural frequency is 2 pi 4 hertz. Line 6 and 7 find Kp and Ki based upon the damping and the natural frequency. And then I generate a transfer function in 8 of the PI controller. Okay, once I have that, again, 10 through 16, I'm just converting the continuous time Laplace domain to digital. Okay, and again, I do the backwards, I do the zero order hold, and I do the Tustin. And they're just, again, different approximations of the conversion from continuous time or Laplace to digital time. All right, again, I have this kind of same code block here. What I'm doing here is, again, from these filters, I'm actually calculating the fixed point, the Q21, the integers you're actually going to have in your C code when you implement this on your microcontroller. It's the same exact code, and you can see here, these are the outputs for both Backwards Euler and for Tustin. These are the coefficients, and again, if you want to check, you can take these numbers to see what they represent. Just take A1 and divide it by 2 to the 21. You'll see what number it represents, and so on and so forth. You can figure out what it represents. These are, again, Q21. Again, I didn't note it last time, but I made Q scriptable. So if you want to change, you don't want to run your controllers with fixed point Q21 numbers, you can change it here, and your coefficients will come out right. All right, let's look at our response here. This will be for Backwards Euler here, this digital controller here. And again, these things are represented by these numbers in Q21. And if you take a look at this, remember this is the integrator, the PI controller. So the output, right away, we're not locked. You can see here we need to speed up. And the PFD is saying speed up for 3 cycles. And then we overshoot. You can see here we need to slow down. And so remember, it wasn't perfectly damped when we look at that example. Speed up, slow down. So we overshot a little bit. And then finally over here, you can see we're kind of locked. We're teeter-tottering for 1 cycle between the two. An interesting thing to note here is, again, the control effort is looks very close to the PFD. It's because we have a PI. It's not really a low-pass filter. We're not low-pass filtering the PFD output. So you see basically a lot of the K action, or the proportional gain showing up, and very little of the integral. I mean, it's there, but it's very little. The other thing I'd like to note is these numbers here, 2 and -2, they are times 10 to the 6. Well, why is that? Because we're now working in Q21. So essentially, this number here represents 1, and this number here represents -1 in Q21 format. And the same goes for the control effort. You can see this is times 10 to the 8, and even the phase, this is times 10 to the 6. So if you took this number, whatever it would be, like for instance this number up here, and divided by 2 times 2 to the 21, you would get essentially 2 pi, or 6.28. Okay, so again, that's the fractional representation for that. Okay, lastly, we have our Tustin approximation for the PI controller, for our low-pass filter, or excuse me, for our single-phase PLL. Same thing happens again. We have 3 cycles of speed up. We overshoot because the damping's not exactly 1. We need to slow down, and then right around this time here, we're pretty much locked. Again, you can see the control effort here is PI. It's not a low-pass filter. It's a strong proportional gain component. And essentially, we lock somewhere after 170 milliseconds or so here in this case. So we're in the lock state over here. Okay. This concludes the section on Q21 format for single-phase PLL. Thank you.